So how do these algorithms work? Well, I'm going to talk about one specific algorithm, and I want to be clear that you need to use a locally produced algorithm that's been validated and verified under your conditions. But the one I have the most experience with is the Virginia Tech Coastal Plain algorithm. And so I'm going to go over that so that you can understand what goes into building an algorithm so you know what questions to ask when selecting an algorithm for your local conditions. So with the Virginia Tech algorithm, there's some inputs that go into calculating the nitrogen requirement as you travel across the field in your sprayer or fertilizer applicator. So the first category are the user inputs. So what we've got is these user inputs up here, days from planting, your yield goal, and the previous nitrogen or starter nitrogen that you applied to that crop. And so that's what you put in before you start applying to the field. But then there are sensor inputs. And so it's going to use the high-end reference area. Virginia Tech algorithm requires that you put a strip out with more nitrogen than the rest of the field got. And this should be, best possible with more than adequate nitrogen, because what we want is to go out there and have that area be the best, greenest area of the field. The low-end reference area is unique to the Virginia Tech algorithm in that you need a strip with 0 nitrogen applied. And then the last thing is, as you travel across the field, you're getting the area currently in the sensor's view. So the first 2 sensor inputs you get when you pull up to that field. The last one you get as you travel across the field. So first I'm going to show you the general algorithm approach. Across the horizontal axis we have the NDVI, and then up the vertical axis we have the prescribed N rate. And what it does is it applies the lowest nitrogen rate to the poorest crop, and then it goes up as the NDVI goes up, and then it reaches a point where it turns back down and nitrogen rate starts to decrease again in the best area of the field. And I'm going to explain why this is. So this algorithm is designed to vary nitrogen rate according to yield potential and nitrogen responsiveness. The sensor is integrating information from the early growing season into this nitrogen decision. And then it's adjusting nitrogen rate to the spatial variation across the field. So it is addressing yield potential and nitrogen responsiveness independently. And in this figure we can see that typically the flat rate is going to end up being somewhere in here. Now a lot of people start to get worried when we say we're going to put a very low nitrogen rate on the low NDVI, and then they get really worried up here where we're putting a lower rate on the best crop because they think, well, that's the best area of my field, I need to put the highest nitrogen rate down. The first thing I'll say is that generally, if everything's working right, you're operating in a very narrow range. So you're not getting these big downturns that we see here. But also there's a very good reason for why we have these downturns. So now we're going to really look at the algorithm and the calculations that are in place. Now this might look like real mathy type stuff and pretty complicated, but I find it's very important to understand in a practical sense that these algorithms have real world meaning. So up at the top, the first thing that we see is that yield with nitrogen, if it's less than the max yield, then the nitrogen rate is going to be equal to the yield predicted if we fertilize minus the yield without nitrogen times the nitrogen concentration, Pn, in the grain divided by nitrogen use efficiency, NUE. And then we add in there the 100 kilograms per hectare, about 100 pounds per acre, that we know we need to kind of prime the system minus what we've already got down in pre-plant. And then there's an else statement. So we say if the yield with nitrogen is less than max yield, we do the first thing. But the else statement says if that's not true, if the equation is predicting a yield with nitrogen that's greater than the max yield, which if we remember is a producer entered input, that we enter as we pull up to the field, that this is the max yield I think I can get in this field, then instead of predicting the yield with nitrogen, I'm just going to use that value that the producer or the applicator entered in there. So at the heart of this algorithm is the yield prediction equation. And there are 2 yield prediction equations. The one for yield if we decide to fertilize, and the yield if we apply no fertilizer. And this is where the local algorithm development is critical, because these numbers are based on local climate factors, local soil, and growing conditions. So as we look up here, we've got yield with nitrogen is equal to 3,500 times E to the power of NDVI, that's the NDVI of the crop currently in the sensor's view as I travel across the field, and remember that's refreshing about every second, times that ratio of the high-end reference area divided by the low-end reference area, the response index we talked about. So response index times NDVI over days from planting. And so this 3,500, that's one of those factors that's developed through local research. The yield if we don't fertilize is simply the NDVI divided by days from planting times 3,500. And so what we've done is taken the response index out because we're saying, well, if we don't fertilize, there's not going to be a response to nitrogen. So let's break this down a little bit more. The response index estimates additional yield if nitrogen is added. And we talked about that before, that if the high end reference area times the low, divide by the low end reference area is say 1.2, 1.5, hopefully it's always going to be more than 1, that you had more green growth out there in the high end reference area than the low end reference area, then that's how much response we'll get to nitrogen. The yield without nitrogen is just the biomass production to date, because remember I said NDVI is really simply a measure, or it's very strongly correlated to biomass production. And that's why the farmer enters days from planting, because we take the biomass that we see today, divided by the days from planting, and that equals the growth we're getting per day. So what the equation is doing in essence is, it said, I've had this much growth up to now, and I'm predicting out future growth over the rest of the growing season. So how accurate is our calibration model? Well, this is the data that Wade Thomason and Steve Phillips down at Virginia Tech produced when they were calibrating that model. And we see that yield on that vertical axis, predicted yield index, that there's a very strong relationship with the equations that were developed for the Virginia Tech algorithm. So let's talk about that end responsiveness that we said. We've talked about yield potential. End responsiveness is a real important part of nitrogen requirement. And so we take that yield with nitrogen that we calculated and the yield without nitrogen that we calculated. The difference between those two is the yield due to nitrogen. So let's say that it calculated 50 bushels per acre extra when I fertilize. So I'm getting 50 extra bushels of grain. The PN is the nitrogen concentration in that grain. So we take yield bushels per acre, and we take pounds of nitrogen per bushel, and we get the pounds of nitrogen in that grain. But we know not all the fertilizer N we apply goes into the grain. Some of it goes into plant tissue, some of it goes into the soils and immobilized. So we divide it by a nitrogen use efficiency factor. Typically we use a factor of about 50% or 0.5. So here's some data from the algorithm predicting yield with and without nitrogen from a real field trial. Again, on the horizontal axis, we've got NDVI. On the vertical axis, we have yield in bushels per acre. And so the difference between those two is that yield responsiveness, because the bottom line is yield without nitrogen, top line is yield with nitrogen. My high end reference area was 0.75, my low end was 0.5, so the response index was 1.5, and we're going to get about a 50% response. Make note that down here at the very low NDVI, we're not seeing very much responsiveness. The other thing to notice when we look at a yield prediction equation, and this is the same data, but I've subtracted the yield without nitrogen from the yield with nitrogen. And so what I'm plotting here is yield responsiveness across the NDVI range. And we see that it starts to go up exponentially to unrealistically high yield levels. In this field, we don't expect to get yields of 300 bushels per acre. So this is where that else statement comes into play that we showed before. We know that yield with nitrogen minus yield without nitrogen goes up exponentially. So we replace the yield with nitrogen that the equation is predicting with the max expected yield, which is a user input. And since that's a fixed value, but now the yield without nitrogen is continuing to go up, the difference between the two is going to start going down because the yield without nitrogen will exceed the yield with nitrogen. So this is the equation in graphical form. On the vertical axis, we see nitrogen rate in pounds per acre. Across the bottom horizontal axis, we see NDVI. Here's the first part of the equation. Yield with nitrogen minus yield without nitrogen times nitrogen concentration divided by NUE plus that starter nitrogen that we need. And then we get up to the point where the yield with nitrogen has exceeded the max yield that the user put in. So the equation is going to automatically substitute in that max yield on the fly. And so if we get an NDVI up above that point, it's going to start lowering the nitrogen rate. So what we've done is we've converted yield prediction from NDVI into a nitrogen rate. We've taken that delta yield or that yield responsiveness and multiplied it times the nitrogen concentration divided by the use efficiency, and that is what gives us the amount of nitrogen that we needed. And then that 100 kilograms per hectare or 100 pounds per hectare is basically what we know we need to kind of start the system or prime the system. So the other key factor here is with these algorithms, the user can set a maximum and minimum based on experience and equipment available to them. For example, most sprayers aren't going to be able to go from 5 gallons per acre up to 50 gallons per acre in a second. So what we typically do is pick a range that we can realistically achieve. But then also there's a comfort factor here, because the hardest thing for the grower to adjust to nitrogen, variable rate nitrogen management is the comfort factor, skepticism, understanding how the equation works. And when they look at this graph, if the nitrogen rate drops off too low, they're just not going to be comfortable with it. So they can set a maximum and a minimum based on their experience, and the equation will constrain within those two parameters, and we'll stay in a range that we're comfortable with. And that's what we've done here. We've set a maximum up about 160 pounds per acre of nitrogen and a minimum down at 40 pounds per acre of nitrogen. And the Virginia Tech algorithm, you can see, is going to go up. And at those very high NDVIs, the nitrogen rate is going to come back down. And the red line shows what the farmer would have applied in this field across that entire NDVI range. So in summary, the Virginia Tech algorithm provides one example of a response index algorithm. It adjusts to temporal and spatial variability and nitrogen requirement based on yield potential and responsiveness. It's going to require reference strips, and in a practical sense, that's the most difficult part of using these sensors. The user should understand the science behind the algorithm and be able to make these informed decisions. It's not plug and play, so this isn't like auto steer. It's not like GPS where you just plug it in and it gives you a number. If you move on to these more advanced technologies, you really need to have an understanding so that you're comfortable with it, you're watching the monitor and the fertilizer applicator, and you're making informed decisions if you see something that you're not comfortable with.